Hello, everyone. Good morning. Welcome to the first session of day 2. So this session is going to be on AMReX solver for phase field simulations. So I'm Nasir Attar. We have Abhishek here with us and also Dr. Chennai. So our team is from C-DAC Pune. And so in case you don't know about AMReX, you don't need to worry. This is going to be an introductory session. So I won't overload you with information. So just have to be present here. Okay, so we'll get started. So let us first begin with the big picture that will set the flow for rest of our talk. So first, you'll be introduced to the AMReX. So what exactly it does, what it is. Then we'll look at few code schematics and few functionalities of AMReX. Then we'll look at how to build the environment for the solver, and followed by few results from AMReX simulations. Okay. So what basically is AMReX? So this part is directly taken from the AMReX documentation. So I've just mentioned few points here, but I mean, in actuality, it does a lot of other things as well. So it is publicly available, supports C++ and Fortran interfaces, multi-dimensional support you have, and you have support for cell-centered, face-centered, so it's up to you. And the main thing is parallelization. So you can do it via flat MPI or MPI plus X. So X can be your OpenMP or CUDA, anything. So AMReX is basically the aim for building AMReX was to have a high performance framework for applications to run on variety of current and next generation machines without substantial architecture specific code development, or the user should not each time update it himself if a new software comes. So here there is some level of abstraction. So the user is hidden from the application and the application is hidden from the architecture. So it's pretty easy to use. So now that we know what AMReX actually is, we'll move on to the code schematics. It's pretty basic, so you'll understand it easily. So this is basically the flow for this part. So when you solve any parallelization problem, a problem using parallelization, you basically generate a domain. Then you cut that domain into smaller parts. Offload these smaller parts onto different processors, and then you compute your solutions, right? So this is basically the scope of your problem, and then you export your solution, and then you can view it. So till exporting this part of the solution, this part of the code, everything should be enclosed between AMReX initialize and AMReX finalize. So a lot of AMReX classes are, defined in these bounds itself. So it's better if you don't write anything outside these bounds. So next, moving to box and geometry. So basically, we have to first create a domain. So we specify some number of cells, and then we'll specify the dimension of the real box, coordinate geometry, and again the boundary conditions. So this is sufficient to define the geometry and the box. Okay. So now that we have the box and geometry ready, we'll move on to chop the box according to our needs. So here you can see the number of cells are 100, and I've chopped it like not greater than 50. So you can see I've created 4 boxes here. So this is basically, the division that is happening. So now that you've divided the bigger box, you can allocate each one to one processor, and you can further do your computations. So when you allocate it to processor, you can use the default order that is being shown here that AMReX follows, or you can also provide an array if you want to customize which box goes to which processor. So you have that freedom. And also multiple boxes can be offloaded to one MPI processor. That can also be done. So now that we've offloaded our boxes, we have to solve for the field variables as described by Professor Guru Rajan yesterday. So if we have to solve the field variables, we have to store them. So to store these variables, so imagine you have a 1000 cross 1000 grid. So it is close to 1 million points. So you have to have huge arrays, right? So AMReX provides multifab. It is basically an array. So to build that array, you don't actually have to specify size and everything each time. You just have to give the box. So it will understand the size on its own. You'll give the mapping, distribution mapping, so that it'll, it will give processor specific arrays to each processor. Then you can give number of components that will come to later, and also the number of ghost cells. So what I mean by number of components is, so for example, let's say I have a 3D array. So I have the dimensions I, j, k that I use to go to a specific location. And I also have another component, 0, 1, 2, 3. So that way you can have a multi-component array. So next thing is the ghost cells. So the ghost cells are important for your boundary operations and also neighbor-to-neighbor communications. So as you can see, the box on the left is 0, 0 to 3, 3. And I've added one layer of ghost cell. So it'll be from -1 to 1 to 4, 4, the new box that is generated. So now that we've given the ghost cells number of components, we've completely built the array that stores the field variables and does computations on them. One more important thing in parallel programming, as we all know, that communication between different processors consumes a major chunk of your computation time. So this usually happens because these calls are blocking in nature. So the fill boundary that you see on the top, it is used to fill ghost cells in AMReX. And the parallel copy you see is to copy one array to other, like huge arrays of your field variables. So usually to avoid this, AMReX also provides non-blocking calls. So you can do no wait, as you can see, parallel copy no wait. So it will not wait. So between your communication, you can overlap some computation. So that way you can, optimize it much more to reduce the computation time. Next, as we have offloaded to different processors, we'll see how each processor computes it, and what is the computational domain for each processor. So as you can see, the red one is our actual box, and the blue is the ghost cells. Okay, so this is how each block looks. So it has a valid box and followed by a layer of ghost cell. So these computations are being done parallelly. So next, what AMReX actually provides is the MPI plus X that I told in the introduction. So the purpose of such functionality is to have a performance portable code. So with constantly evolving HPC environment, we are introduced to new architectures with different capabilities and programming models. So to reduce the burden on the user to constantly learn new architectures, AMReX has a lightweight of abstraction layer. So what it actually does is this layer helps the user to specify what operations they want to perform without actually specifying how these operations are done. Okay, so for example, here we have, the center domain, small domain that you see, you've offloaded it to some using MPI to different processors. Now, if I zoom on to one box, now I can tile it. So basically tiling is cache blocking. So you can use OpenMPI threads for doing that. Or on the other side, you can use GPU parallelization, where you can offload bunch of your cells to the threads that are there in GPU. So if you use MPI plus OpenMP, then it'll use OpenMP threads. But if you use MPI plus CUDA, then it'll go to GPU parallelization. So it's that easy. Now, how to do that? We'll we'll arrive at it later. So one more thing about the abstraction is the parallel for in AMReX. So it is an iteration loop. So the important part is this. Okay, so AMReX GPU device. So let's say I'm building my model with GPU support, or let's first start with without GPU support. So if there is no GPU support, this part will seamlessly work on a CPU, no issues. But if I build it with GPU support, then this will actually act as a kernel and it will launch GPU threads. So user is again at ease here. So you don't have to each time change your code again and again for running it on CPU or GPU. So you can have one single code that you can directly change the environment variables, and then you can run it easily. So now that we know what AMReX basically does is, so we'll look at how we can build the environment. So this is one important part where we actually have to look at the make file of AMReX and again make.package. So this is how a basic makefile looks for AMReX. So you first begin with introducing the path to the AMReX directory, followed by followed by few other paths to make.def and everything. So the important part here you see is this, the one that is highlighted. So these are actually flags. So when you build with debug false or true, I mean, you can turn it on or off. So dim that you see is the dimension of the problem. Comp is compiler, and you have bunch of different options. So this is directly taken from the documentation of AMReX. So you have these many options. So you can turn it on, off, anything you want to do. So if you want to build it with GPU support, you simply have to turn, you can see use CUDA, true. So it is built with GPU support. If you use false, then it's normal CPU code. So the other thing that is important in makefile is this make.package that you can see. So basically, this is the outline of make.package where you, I mean, mention your source files and header files. Apart from that, you can define the compiler and also the MPI that you're using. So it is essentially helpful when you're running on clusters or something. So if you want to use different compilers, then you can do it. So now that we've built the environment, understand the code schematics, and we know what AMReX is, we'll look at few results that we have generated using AMReX. Okay, so on the left that you could see this. Yeah, this is a heat diffusion equation. So you have some temperature at the center and then it diffuses, and this is the spinodal decomposition. So these are written in AMReX. So spinodal is also there in the MicroSim repository as an example for you to understand the code, because the formulation is pretty easy. And I've also shared the manual, I mean, within the folder, so that you can understand the formulation as well as the discretization that is being done. Next, we'll move on to so how we've incorporated AMReX into MicroSim is we've used the grand potential model as described by Professor Abik yesterday. So we've used grand potential model and we've written the code in AMReX. And here you can see this is a three-phase simulation for 13 Kelvin undercooling. So one dendrite is at 0 degree rotation and other one is at 45. This one you can see is a two-phase simulation. So one dendrite is placed at corner with 45-degree orientation and it grows. So 7 lakh iterations were done to achieve this. So next we'll look at scaling of our code and the performance of our code. So we've plotted the computational time versus the number of cores that we've used. The simulations are again done for 13 Kelvin, 7 lakh iterations. So as you can see, when we ran on 96 cores, we have a time about 122.32 minutes. Okay, so when we increase the number of cores 5 times to 480, we also received approximately 5 times speed up, which is 4.95, which is pretty linear. So it's decent. And we've again increased the number of cores twice compared to 480 to 960, and we've again received a 1.87 times speed up. So this shows that the scaling is pretty linear and it's good. So if you're into solving time and work problems, if you like solving it, this would be an ideal fit for you. So again, another scaling that we want to do is with the domain size and number of processors. So the left one you see is 1000 cross 1000 grid. Okay, the simulations are done on 96 cores, and the right one is 2000 cross 2000. So the left one is 1 million cells and the right one will be 4 million, right? So it is 4 times scale up, right? So 96 processor will do into 4, so we'll get 384 processors. So this was run on 384 processors, and the time that you can see is pretty close. So this scaling is also it's also working fine. So now that we've looked at few results, we'll now move on to hands-on implementation, and we'll try to learn how AMReX works and how Singularity is incorporated and everything is done. So yeah, these are the resources that you can refer to. but I would recommend that you first try few problems hands-on, and then you go through the code, and then you try to understand it. Because if you directly jump to the paper, I mean, it is pretty difficult to grasp it that way. The last one that you see is the link to the documentation. So documentation is pretty detailed, so it will also help you to learn new things that AMReX does. And I've only highlighted very few aspects of AMReX. I mean, in reality, it's in great detail. So you have a lot of options to work with GPUs, a lot of things that you can customize on CPUs as well. So yeah, thank you. That's about it for my talk. So if you have any doubts, you can contact me. I have shared my email address, and we'll now move on to the demonstration. Thank you. Just a second, I'll share my screen accordingly, and then we'll move on to the demonstration. If you have any doubts, please type it in the chat box, or you can directly ask it here. Anyone who is trying it out here? Okay. So I've shared the link in the chat. So people who want to try it, I mean, there's a proper procedure that you have to follow. So once you follow it, I mean, it's pretty easy to run. Yes. So I mean, as we have seen yesterday, that we first begin by installing the Singularity. So we'll also get the connection. One more thing that you'd be interested in. So you have to pull the local, the latest repository. So I've made changes yesterday. So if you're trying it out, just get the latest MicroSim. You can simply do a git pull, or click on the link below that is mentioned in the document, and get the latest update. So yes, and also the CIF file that is present here, it's shared with you. So the access is public, so you can directly download it. So where to download it, I'll show it to you. So let's say I've created a dummy folder that is workshop. So in that I have MicroSim and also the CIF file and Singularity. Okay, I'm sorry about it.
This zip file, is it there in the folder?
Yeah, it's there. It's there. Everything is there. The link is there.
Okay, okay.
Okay, okay. Okay. Yeah. Also, Swapnil has shared the document, the Google Drive link with you, so you can also get it there. Okay, so I hope everyone can see my screen. Is anyone in the meeting? Okay, yeah, so yes, so first we begin with installing the depth file that we've already done yesterday. So moving on, we'll next get the latest MicroSim repository. Also download the CIF file, it is there. And so now in this folder, here you can see that we have the CIF file, we have MicroSim folder as well. Okay, so and this is the latest folder that is there, the updated one. So if you want to run, yeah. So to run, you will have to run the singularity command that is there, singularity shell bind microsim. So I'll just copy this. So after I run this, you can see there's singularity written. So we've entered the singularity. So now what we do is we go to this folder. As we have mentioned, the step 6 that we're doing is you go to mount folder, where you can actually type Python. Yeah. Okay. So Python 3 microsim. So this is to load the GUI that is there. So once I mean the files are imported, you can see the GUI. Yeah, this is the basic GUI that is there. So we'll first import the in file that is there in the AMReX folder. We'll go to GP AMReX. Here you can see there's an input.in. I hope this is better. So this is better. So as you can see, there are a few parameters are missing. So we'll add them, no issues. So first we'll begin with the domain size. So let's not make it 1000 cross 1000 as we're running on a small system. So we'll make it 100 cross 100. Okay, so the dimensions are 2. And we also have the delta x, delta y, and also the time. We've set it. We have the number of phases. Again, change phase name. You can name it accordingly, the way you want it. And also the number of components. We'll set the number of time steps to say 20,000. This save at is for the checkpoint file. So in case your simulation is stopped in the middle, and if you have a checkpoint file, you can restart your simulations from there. So right now, let us say we'll have it at 20,000. Some workers will run on 2. Yes, so these parameters are already filled as we've imported the in file. So we have diffusivity for liquid as well as solid already taken. So here we have gamma. So functional properties will look at it. So we're using F4 for AMReX. So right now, this is the only function that we have. The equilibrium, C-fill, guess, and also the rotation matrix is properly filled. Next, we'll look at the boundary condition. So on all sites, it is going to be Neumann. Yes. So now we'll import a shape. So we already have a filling file. I mean, you can generate it as well on the go. So yeah, so like 0, 0, the radius of the cylinder is 5. Z start and Z end is 0 again. So it's a 2D simulation. We go to the next. So here there is one trick that you want to add is you first have to click on grand potential for you to see the grand potential written on the top, and then move to GP AMReX and then go to next. So I mean these keys were recently added, the GP AMReX and GP OpenFOAM. So the update, I mean it will be soon updated to directly locate. So we have gamma ABC that's not there for two-phase simulations. We have equilibrium and filling. Okay, let's start with page 1. Yes, so this binary isothermal track progress is the plotting frequency of our output times. So we'll keep it to 1000. Row is there. Let's put some value. Okay. We are not shifting the domain, so we don't have to worry about it. And simply next. So now that I mean we've given everything as the input, we'll let us name this as input underscore A and filling underscore A, just so that you can distinguish between the pre-existing input files and filling files with this one. So we'll click on generate. So where to generate? So in the executable folder that is uh, inside grand potential AMReX. So yeah, as you can see, the files have been successfully created. Okay. Yes, so now we'll close this. Yeah, we're still in the singularity. So let us locate to the grand potential folder. So as you can see here, we have filling underscore A and input underscore A as well. So the files have been generated. So for you to run, you have to run it via terminal for time being. So let us first update the bash file that is there in the terminal. So this /replace that you see, it's actually important because you have to change the file according to AMReX. I mean, the way it reads, it's a small change. You don't have to worry about it. I've just changed the name of the files, and also we'll have to look at the number of processors once again, because this is a running command. So we plan to run with 2 processors. Okay, that's everything is done. So I'll basically tell about the make command. So you basically build your object files and everything is built from the main AMReX repository to here. Then you build a replace file. Replace file is basically to change the input file according to AMReX. That's it. And then you simply generate the input file that is suitable for AMReX, and then you run your problem. I'll save this. Okay, now let's see, we'll run the bash. Okay. What you can see right now here is main.o or other files. These are basically the object files that are being created. So every time you do a new make, these files will be created. So it will take some time, but it's okay. So we'll wait for some time. Yes, so now make is complete. These are just few output values for you to check that your parameters are right. So as you can see, advanced step 1000, 2000. So it's running. The checkpoint file is the starting checkpoint file, and one you'll see at the end of the simulation as well. So we ran it for actually 20,000 simulations. So we'll wait till then. Yeah, so after you complete your simulation, you also get this runtime, which is in seconds. So I mean, you also get your execution time basically, so which is a good thing. So we'll now check if the input, if the plot files are generated. Wait. Okay, here you can see plot 0, plot 1000, and all. So the plot files are generated. Now we'll come out of Singularity, and we'll view these in the MicroSim post-processing tool. Okay, so now we're out of the Singularity. Let us locate to the MicroSim folder. So you can also view these files in different post-processing software. So Paraview also supports it. So we'll first start by taking the input file. So if you remember, our input is input underscore a dot n. So this is what we'll select. So now we've selected the input file. So now you can see there are a number of components is defined. What is the name of the components? It is also defined, the number of phases and also the name of the phases. So that's why you need the input file first. Then we'll actually convert our files to VTK. So how to do that? I'll show you. So again, we'll have to locate the N file to begin. Yes, we have located the N file, and you have to click on the PLT that you see there. So as AMReX has the plot file format specified, AMReX can also output an H5 format. That is also possible. So let's say I'll select the first file. Open. Okay. The start time, I'll put it as 0. 0 is the start time. We'll take the step to be 1, and the end time going to be 20,000. As we ran for 20,000 iterations, and the last plot file is 20,000. We're not giving any name to VTK, so let it handle on its own. So as you can see, it's saving all the VTK files. So it is saved. We'll look at them. Yes, so here you can see that the VTK files are generated. So the conversion is done, I mean, pretty quickly. Okay, there might be some issue with this. Yeah. Okay. So I'll check the filling file just a second. Yeah, it's there. It's a 5 number of cells. 0, 0. Yeah. Corner. Yeah. Yeah. Okay, so I've taken the input, will import VTK. Okay, now, there's a problem because I think it was problem converting during the converting file. So no need to worry. I'll again demonstrate it to you with other VTK files that I've already generated as backup. So let's locate to that folder. Okay, so not there. So I'll probably start. Okay, yeah, we have the VTK files. I can directly load them. We don't have to go through this process again and again. So I'll just show it to you. Yes, so as you can see, plt.vtk. So we have 10 files. So let's first begin with this. Yeah, so if you can see, I don't think you can see, but there is a small seed at the corner. So if I play, it will evolve. I mean, this is for 1000 cross 1000, and also the evolution is pretty, limited to few number of steps. So that's why you can see only a small seed. You can't see the entire dendrite. For that, you'll have to run it for larger number of iterations. So as this is a smaller system, I've not ran it for a larger number of iterations. And also with the MicroSim post-processing tool, you get a few options, such as you can plot velocity over line. So let's say my dimension for this problem is 1000 cross 1000. Let's say I'll select a diagonal line, which will be 999, comma 999. Okay. Yeah, you can see that I've received the velocity over the line, which is going diagonally from 0, 0 to 999, 999. And we also have tip radius. And again, I mean, this is a very small simulation. So, I mean, if you run on a large system, then you'll get a proper curve. Okay. So yeah, that's about it. So this is the post processing. You can also view these files in ParaView. I'll just show it to you. And one more thing, I'll show it to you as how our domain decomposition is done. So you'll appreciate it in ParaView. So, yes, so the plot files are taken. So this representation that you see outline, it is basically the box array. or how we chop the bigger box into smaller boxes. So I've chopped it into four smaller boxes. So that's what you can see here. So let's say if you have, I mean, divided into like even further smaller boxes, you'll see it here as well. And right now, all the AMReX solvers are single level solvers. So we're not doing the adaptive mesh right now. So if you were doing adaptive mesh, so if you select a specific level, you can also see the outline or the domain decomposition or the box array at that level. So we have three options. We can view alpha, we can view liquid, or we can also view mu. So we'll select alpha and we'll select the surface that we want to see. Okay. So as you can see, it's the same thing that we saw in the MicroSim post-processing tool. And MicroSim post-processing tool also gives you the options to view multiple profiles. So you have alpha, you have liquid. So basically, it's the inverse. And also you have mu. Yeah, this is the mu that you can see. So yeah, that's about it. You can, I mean, try using AMReX. I mean, it's pretty easy to use. If you have any issues, you can contact us. So yeah, if you have any questions, I mean, we've put a major time for questions because you can't really appreciate without asking questions. Yeah.
What is the difference between, let's say, the grand potential MPI implementation and
Yeah.
AMReX implementation?
There's no difference.
In the runtime and results, it will just be.
Yeah, it'll just be the same. It's just how the software handles the resources. Okay, there the code has been written specifically for MPI and everything is done. I mean, on a, I mean, if you're a user who is not aware about MPI or anything, yeah, exactly. So it's difficult for you to write such codes, such huge codes. Like Abhik sir has written a huge code. Okay, so if you're working on AMReX, I mean, you can literally bypass everything. You can just understand the gist, and then you can solve your problem. So without understanding in depth that how the communication is done, you have to wait.
The domain decomposition is automatically.
Yeah, yeah, yeah.
The sharing between the host cells that
It'll do automatically. So as you remember, if I mentioned fill boundary, okay, so that fill boundary command itself fills all the ghost cells and the neighboring communication as well. Yeah, so you just write it and everything is done. So you don't actually have to worry about it.
And because of that overhead, is there any runtime loss?
No, 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 no. So to avoid that, you also have no wait, right? So you can push your computation between the communication. Yeah.
But we did not have, like, if you have this, let's say, 4x4 array,
yeah,
and you have two host cells.
Mm-hmm.
Let's say if you have this Laplacian 5 point sensor, you're using the point from this host cell, right?
Yeah.
If it gets updated,
Yeah.
you're using from T and T plus 1 as well.
No, the
No.
updation is happening before every iteration.
Before the update happens. Yeah.
Okay.
So we fill it before, and then we compute everything, and then we flush out the solution, and then we again update it. Yeah, with the new fields. Yeah. Yeah. So any other questions for the online participants as well?
See the chat, put it in the chat box. Nasir, just tell the participants to put their questions in.
Yes. Hello, the participants. You can put your questions in the chat.
This one is asking.
Oh, can you show your job submission bash file again? Okay, so you can locate it in the AMReX folder itself. So I'll show it to you. Just a second, I'll share my screen. I hope my screen is visible. We'll go to the MicroSim post-processing, like MicroSim repository. So the bash file that is present in the repository, you can check it. I mean, this is the job submission script. So you go with make, then there's some changes to the input file, and then you run the problem. I hope that answers your question. Yeah, yeah, that I've discussed. I hope that answers your question, Kumar, Akash.